problem we want to solve this week is as follows. We want to know how many subsets with 3 elements can be formed from the set of the first 20 counting numbers such that 4 is a factor of the product of the 3 numbers in the subset. For example, here's a list of subsets with 3 elements that can be formed from the set of numbers 1 through 20. And this subset satisfies the criteria because 2 divides 2 and 2 divides 6, so 4 divides the product of these 3 numbers. 2 times 6 times 5, which is 60, and 60 divided by 4 is 15. So this is an example of the kind of subset we're looking for. Here's another subset, and 4 divides 16. So 4 certainly divides the product, and 16 times 1 times 3 is 48, and 48 divided by 4 is 12, which is a whole number. So this subset satisfies the criteria. So we're trying to count subsets like this. How many are there? On the other hand, here's an example of a subset that doesn't work. This doesn't work because all the members of this subset are odd, and so the product is odd. 1 times 7 times 9 is 63. So 63 is not divisible by 2. So it's certainly not divisible by 4. In fact, 63 divided by 4 is 15.75, which is not a whole number, so this subset does not work. And this subset doesn't work either because while one of the numbers is even, it's not divisible by 4. And so the product, 5 times 2 times 11, is 110. And 110 divided by 4 is 27.5, which is not a whole number. And so this subset doesn't work. So I've listed 2 subsets that do work, and the problem is asking how many subsets like this are there? The solution for this problem involves the concepts of permutations and combinations. To explain this concept, let's first solve a simpler version of this problem. So the basic problem here is that we want to know how many subsets we can make from a given set. A similar but simpler problem would be as follows. How many subsets with 3 elements can be formed from the set of the first 20 counting numbers? So we would be asking how many subsets like this can we form, regardless of whether the product can be divisible by 4 or not. This is not a difficult question, and there is a formula for this, but if we were trying to count the number of subsets by hand, it's a pretty big problem, especially if you've never worked one of these problems before. So, in order to be able to understand how the formula works, how about let's first consider an even smaller problem as follows. So how about we consider trying to figure out how many subsets with 3 elements can be formed from the set of the 5 letters A, B, C, D, and E. This problem is small enough that we can even make a list of all the subsets and count them. That gives us a way to compare the formula we derive with the correct answer. Now, one way to go about solving this smaller problem is to make a tree and consider all of the possibilities, like this. So if we have a set of the 5 distinct letters A, B, C, D, and E, and we want to create all the possible subsets consisting of 3 elements, we can go about it in a methodical fashion as follows. First, choose a letter to start with. For example, let's start with the letter A. After that, we see that there are 4 ways that we could choose the second letter: B, C, D, or E. And after that, in each case, there remain 3 ways to choose the third letter. For example, if my first letter is A and my second letter is B, then I have 3 letters left that I can choose for the third letter: C, D, or E. By following the path through the edges of the tree, from the root down to the leaves, we can read the subsets that we've found. For example, A, B, C, A, B, D, A, B, E, or the set A, E, D, and so on. We can repeat the same process and make a tree starting with any of the 5 letters A, B, C, D, or E. We can see that this method overcounts the number of subsets because of all the possible ways we could permute the 3 elements in each subset. So a set like A, B, C is the same as a set like A, C, B because these 2 sets consist of exactly the same 3 elements, A, B, and C. So if we take the curly braces off of these sets, we can see that making a set of trees like this is actually giving us the number of permutations of 5 distinct elements taken 3 at a time. That is, we have 5 ways to choose the first letter, and then times 4 ways to choose the second letter, and then times 3 ways to choose the third letter. Really, the quantity we seek is the number of combinations of the 5 distinct elements taken 3 at a time, irrespective of the order in which the elements are written. We can show how the permutations are related to the combinations by making a table like this. So for each possible subset with 3 elements, we can permute these elements in 6 different ways, because for a set with 3 letters in it, there are 3 ways to choose the first letter, A or B or C. Then for each of those choices, there are 2 ways to choose the second letter, and then for each of those ways, there is 1 way to choose the third and last letter. So that gives us 3 factorial, or 3 times 2 times 1, which is 6 permutations of the 3 distinct letters in the subset. But each of these entries in this row represents the same set, because each set consists of exactly the same 3 letters, A and B and C. And this is true for each row in this table. Each row gives us 3 factorial, which is 3 times 2 times 1, or 6 copies of the same set. And when you take the curly braces off, we get 6 different permutations of the 3 letters in that row. So I made the number of rows in this table equal to the number of combinations of 5 distinct elements taken 3 at a time, which is the same as the number of subsets with 3 elements that can be formed from the set of 5 letters A, B, C, D, and E. And the number of columns in this table is equal to 3 factorial, which is the number of ways that we can permute 3 elements. So if we take the curly braces off, this table gives the collection of all the permutations of 5 distinct elements taken 3 at a time. So on the one hand, the number of permutations of 5 distinct elements taken 3 at a time is equal to the number of entries in this table, which is the number of rows, times the number of columns, or 5 choose 3, times 3 factorial. But on the other hand, this quantity, the number of permutations of 5 distinct elements taken 3 at a time, is the same as the number of leaves in the 5 trees shown in this diagram, which, recall, is 5 times 4 times 3. So in this equation, we can solve for the number of subsets containing 3 elements by dividing this equation on both sides by 3 factorial, like this. So dividing both sides of this equation by 3 factorial, we can solve for the number of combinations of 5 distinct elements taken 3 at a time as follows. It is equal to 5 times 4 times 3 in the numerator and 3 factorial, or 3 times 2 times 1, in the denominator. And because of the common factors in the numerator and the denominator, for instance 2 goes into 4 twice and the 3's cancel, this ratio reduces to a value of 10, which is the answer. This does give the same number of rows as in my table, like I showed you before. Right here. You might try listing all of these subsets yourself and check your answer against my results. With a little bit of thought, you can see that every problem of this sort can be solved using this same method, so that the number of combinations of n distinct elements taken k at a time is equal to the number of permutations of n distinct elements taken k at a time, divided by k factorial, or the number of ways that you can permute k elements. So as far as answering the smaller problem is concerned, we're done. The number of ways to form subsets with 3 elements of the set with 5 distinct elements in it is 10. However, let me take this formula one step further and show another useful way to write this formula which is how it's commonly written. So what I'm going to do is I'm going to look at this numerator, 5 times 4 times 3, and keep multiplying down all the way down to 1. And whatever I multiply the top, I have to multiply the bottom by the same thing. And let's see what happens. What happens is that the numerator becomes 5 factorial, and in the denominator we get 3 factorial and 2 factorial. And the 3 and the 2 add up to 5. And this formula always works out this way. And because of the symmetry of this formula, we can see that this quantity is also equal to the number of combinations of 5 distinct elements taken 2 at a time. If we think about it, the symmetry of this formula is not too surprising, because if we have a box containing 5 distinct elements, then the number of ways that we can take 3 elements outside of the box and form a set of 3 elements is the same as the number of ways that we can leave 2 elements inside the box and form a set of 2 elements. Now, one more thing. You may think, oh, we're getting tired of saying the number of combinations of 5 distinct elements taken 3 at a time. So it's a very common terminology. We can say 5 choose 3 for short, or this is 5 choose 2. This method of counting reveals how we might solve this problem for sets of any size. So this formula generalizes as follows. So generally, the number of combinations of n distinct objects taken k at a time is equal to this ratio, with n factorial in the numerator and k factorial and n minus k factorial in the denominator. Again, we note that the symmetry of this formula tells us that n choose k is the same as n choose n minus k. Understanding this symmetry can sometimes save you work computationally. And this symmetry is reasonable because if we have n distinct elements inside a box, then if we take k elements out of the box, we're left with n minus k elements inside the box. In case you wanted to know, the derivation for this formula is the same as before. The number of permutations of n distinct elements taken k at a time is equal, on the one hand, to this quantity, which is equal to the number of leaves in n distinct trees like this. So if you have n distinct objects, you have n ways to choose the first object, but once you've chosen your first object, you only have n minus 1 objects left. And then after you've chosen your second object, you only have n minus 2 objects left, and so on down the line until you have chosen k minus 1 objects and so you only have n minus k minus 1 objects left. So the number of ways to permute n distinct objects, taking k at a time, is n ways to choose the first times n minus 1 ways to choose the second times n minus 2 ways to choose the third, and so on down the line. And then the number of ways to choose the kth object is n minus the quantity k minus 1, because we chose k minus 1 objects before we chose the kth and final object. So on the one hand, the number of permutations of n distinct objects taken k at a time is equal to n times n minus 1 times n minus 2 times, and so on all the way down to n minus the quantity k minus 1. But on the other hand, the number of permutations of n distinct objects taken k at a time is equal to this quantity, which we get from a table like this, where the number of rows is the number of choices of n distinct objects taking k at a time, and the number of columns will be k factorial, the number of ways that it's possible to permute the k distinct letters in each row. And the number of elements in that table will be the number of permutations of n distinct objects taken k at a time, or the number of rows times the number of columns, which is n choose k, times k factorial. And so then from this equation, in the same way as before, we can solve for n choose k by dividing both sides of this equation by k factorial, and we get n choose k is equal to this quantity divided by k factorial, and then multiplying by n minus k factorial in the numerator and the denominator, just like before, we get the general formula for n choose k, which is n factorial in the numerator, and in the denominator we get k factorial and n minus k factorial. And this is the formula that we will need to help us solve the problem of the week. Before we solve the problem of the week, let's practice using this formula to solve a few more examples. And I promise the following examples will be used to help us solve the problem of the week. So the first example, we want to know how many subsets with 3 elements can be formed from the set of even numbers from 2 to 20. And the answer is that we are looking for the number of combinations of these 10 distinct objects, even numbers in this case, taken k equals 3 at a time. So for this example, n is 10 and k is 3. And we are looking for the quantity 10 choose 3, like this. So n choose k is 10 choose 3, and the formula for this is 10 factorial in the numerator and 3 factorial in the denominator, and the other number, factorial, that we need to put in the denominator is 7, because 7 is 10 minus 3, and these two numbers that we take the factorial of in the denominator have to add up to the numerator, and 3 and 7 is 10. And that's the way this formula works. It always works that way. And now when we want to calculate this out, it's easy to calculate by hand. 10 factorial is 10 times 9 times 8 all the way down to 1 in the numerator. 3 factorial is 3 times 2 times 1, and 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1, and a lot of cancellation going on here. So I picked the biggest number to do the cancellation. So 7 factorial, 7 times 6 times 5 times 4 times 3 times 2 times 1, cancels with the 7 factorial in the numerator, and all I'm left with in the numerator is 10 times 9 times 8, and the denominator is 3 times 2 times 1, and this is easy to compute. So we're getting 10 times 9 times 8 over 3 times 2 times 1, and this reduces to 10 times 3 times 4. I got the 10 from the numerator, I got the 3 from 9 over 3, and I got the 4 from 8 over 2, and this is 3 times 4, which is 12, times 10, which is 120. So the answer is 120. That means there are 120 subsets with 3 elements formed from the set of even numbers from 2 to 20. For example, the set 2, 4, 6, the subset 4, 8, 16, and the subset 10, 12, 20. Those are 3 examples of such sets. There are 120 subsets like that. The second example is very much like example 1. We're just practicing that combination formula. So we want to know how many subsets with 2 elements can be formed from the set of odd numbers from 1 to 19. So this time we're taking the combinations of n equals 10 distinct objects, odd numbers this time, taken 2 at a time. So we're forming sets like, take 2 odd numbers from this set, 9, 17. What's another example? 5, 11. Sets like that. So how many subsets with 2 numbers formed from this set can we get? I've found 2 so far. What's the total number we can get? That's the question. And the answer again, we're just going to apply the formula like this. So n choose k is 10 choose 2 because n is 10 and k is 2. And the way that formula works, you put 10 factorial in the numerator and 2 factorial in the denominator, and then what else do we put? 8 factorial in the denominator, because 2 plus 8 is 10. And then if we expand the numerator and the denominator out, we see a lot of cancellation going on. So 10 factorial is 10 times 9 times 8 factorial. And we have an 8 factorial in the denominator, which is going to cancel with the 8 factorial in the numerator. And what have we got left? We only have 10 times 9 in the numerator and 2 times 1 in the denominator. Very easy to compute this number. 10 over 2 is 5, and 5 times 9 is 45. Like this. And so the answer is that there are 45 sets just like this that you can make from this set of 10 odd numbers. The third example is just the same as the first 2 examples. Just keep practicing that n choose k formula. So this time we want to know how many subsets with 17 elements can be formed from the set of the first 20 counting numbers. So this time we're taking the combinations of n equals 20 distinct objects, taken k equals 17 at a time. So we apply the formula like this. So n choose k is 20 choose 17 this time, which is 20 factorial in the numerator and 17 factorial in the denominator. And what's the second number in the denominator? It's 3 factorial, because 17 plus 3 is 20. And then, if you expand the numerator and the denominator, we have 20 factorial in the numerator, 17 factorial in the denominator, and 3 factorial in the denominator. And I like to cancel the larger number because it leaves me with less numbers in the numerator and denominator when I'm done. So that is, the 17 factorial in both the numerator and the denominator will cancel out, which leaves me with 20 times 19 times 18 in the numerator and 6 in the denominator, like this. And this ratio reduces to 1,140. It's a big number, but the arithmetic isn't too difficult because of all of the cancellation with the common factors in the numerator and the denominator. So for example, 20 over 2 is 10. 19 doesn't cancel with anything, so I write that down. And what's left is the 3, and 18 over 3 is 6. So all I have to do is multiply 19 times 6 and then times 10 to get 1,140. And notice from the symmetry of this problem that the number of subsets with 17 elements that can be formed from this set is the same as the number of subsets of 3 elements that can be formed from this set. Because remember, if I take 17 numbers out of the box, I leave 3 numbers behind in the box. And notice that this answer, 20 choose 3, is the answer to the simpler problem, which I mentioned earlier. So we've just answered the simpler problem, how many subsets with 3 elements can be formed from the set of the first 20 counting numbers. So again, that answer was 20 choose 3, and we got 1,140. And the smaller problem, which was the very first problem we did, and we were able to actually list all of the subsets, and this was how many subsets with 3 elements that we can form from the 5 letters A, B, C, D, and E. So that was 5 choose 3, and we got the answer of 10. And just a word about notation. So this is just another way to write 20 choose 3. I write the numbers 20 and 30 vertically, like this, and then put parentheses around them. I did the same thing with 5 choose 3. I put 5 on top and 3 below and put parentheses around them. This is another very common notation for the combination notation. There are other notations as well, but these are the 2 that I tend to use, and actually I tend to use this notation more often than this one. But this notation is just a little bit tricky sometimes. People forget and they put a little bar and think that that's a fraction. But there's no bar here, so you don't do this. So that's not correct, because that would be 20 divided by 3, which is equal to 6.66666 repeating. And that's not a whole number, and that's not at all the same as what we mean by 20 choose 3, which is 1,140, which is much greater than 6.666. So this is not a correct notation. So if you use this notation for the combination notation, then be careful and don't put the bar there, because this is not a ratio. It's the combination notation. So by this point, we have answered the simpler problem and the smaller problem that we mentioned at the very beginning of the video, and we've practiced the combination formula for a few examples, and we're almost ready to solve the problem of the week. Let's look at just a few more examples to give us the complete set of tools we need to solve the problem of the week. So 3 more examples, and then we're ready to solve the main problem. The next set of problems demonstrates how to create sets from 2 disjoint sets of objects. For example, how many sets can be formed by taking 3 letters from the set of letters A, B, C, D, and E, and 1 number from the set 1, 2, 3, and 4? And the solution goes like this. Well, there are 5 choose 3 or 10 ways to choose 3 letters from the set of 5 letters, and there are 4 choose 1 or 4 ways to choose 1 number from the set of 4 numbers. So the answers just multiply. So the answer is 5 choose 3 times 4 choose 1, which is 10 times 4, which is 40 sets. I have a visual for that. So here's my table, which I used to demonstrate the answer to this problem. And in the first column, I've put the 5 choose 3 different ways that I can form subsets containing 3 elements from the original set of the 5 letters A, B, C, D, and E. And along the top row, I have the 4 different ways that I can choose 1 number from the set of numbers 1, 2, 3, and 4. Now if I take the union of any 2 of these sets, for example, A, C, D, and 3, this gives me 1 way to form a set containing 3 of these letters and 1 of these numbers. And every single possible way of doing that is somewhere in this grid. For example, here's 1 way that I could form the set B, C, D, union with the number 2. And every one of these entries in this table is different. So the total number of ways that I can form a set choosing 3 letters from A, B, C, D, and E, and 1 number from 1, 2, 3, 4, is the number of rows in this table times the number of columns, which is 5 choose 3 times 4 choose 1, or 10 times 4, which is 40 entries in this table. Example 5 is very much like example 4, same kind of problem, just practicing how we get the answer to that. So the question is, how many sets can be formed by taking 2 numbers from the set of even numbers from 2 to 20, and 1 number from the set of odd numbers from 1 to 19? And the solution looks like this. There are 10 choose 2 or 45 ways to choose 2 even numbers from the set of 10 distinct even numbers. And there's 10 choose 1 way or 10 ways to choose 1 odd number from the set of 10 distinct odd numbers. And since these 2 sets are disjoint, the possibilities multiply. So the answer is 10 choose 2 times 10 choose 1, or 45 times 10, which is 450 ways to choose 2 numbers from this set and 1 number from this set. So for example, we could choose 2 numbers from this set being 12 and 20, and 1 number from this set, say 9, and that's an example set. And there are 450 ways that we could do this. Thank goodness we don't have to count them all, but we have a formula that allows us to calculate how many sets like this there are. And one more example. Example 6 is just like example 5 above. How many sets can be formed by taking two numbers from the set of odd numbers from 1 to 19 and one number from the set of even numbers which are divisible by 4 from 4 to 20? And the solution goes like this. Well, there are 10 choose 2 or 45 ways to choose two odd numbers from the set of 10 distinct odd numbers here, and there's 5 choose 1 way to choose one number divisible by 4 from this set of numbers here. And since these two sets are disjoint, so there's no overlap, they don't share any numbers in common, then the answers just multiply. So the answer is 10 choose 2 times 5 choose 1, or 45 times 5, which is 225 ways that we can do this. So for example, we could choose two numbers from this set, say 3 and 11, and one number from this set, say 8. And this would be an example set. The total is there are 225 ways that I could choose a set like this. As promised, we now have all the tools we need in order to solve the problem of the week. And we'll find it's quite easy to solve with the correct application of the combination formula. So here we are again, back to the problem of the week. How many subsets with 3 elements can be formed from the set of the first 20 counting numbers, such that 4 is a factor of the product of the 3 numbers in the subset? I'm going to give 2 possible solution methods and then compare and contrast the two. The first solution method, I'm calling it the direct solution method. We're just going to count all the ways that you can choose 3 numbers from this set so that 4 is a factor. The indirect solution method, we're going to count all the ways to choose 3 numbers so that 4 is not a factor, and then subtract this result from the total number of ways to choose the 3 numbers. I'm going to start with the direct solution method, like this. For the direct solution method, we want to count all the ways to choose 3 numbers from this set so that 4 is a factor of the product of the 3 numbers. So let's consider all the possibilities, like this. What are all the possibilities that we could choose 3 numbers from this set? Well, all 3 numbers could be even. In that case, 4 is a factor of the product of those 3 numbers. Or, 2 of the numbers could be even and one of them is odd. In that case, 4 is a factor of the product. Or, one of the numbers could be even and 2 of the numbers could be odd. But if we want 4 to be a factor of that product, the even number would need to be divisible by 4. And finally, the last possibility, none of the numbers are even, so all 3 numbers are odd. Now, we're going to cross this out because in this possibility, if all 3 numbers were odd, then 4 would not be a factor of the product. So of all the possibilities, really, there are only really 3 ways that we could choose 3 numbers from this set and the product being divisible by 4. And these are the 3 ways that that could happen. Let's count how many ways there are for each one of these possibilities in turn. Okay, what if all 3 numbers are even? How many ways can we do that? So I need to choose 3 even numbers from the set of numbers 1 to 20, which for convenience I've arranged in a little grid like this. 1, 2, 3, 4, 5, 6, 7, 8. I'm counting like that. So I've put all the odds above and all the evens below. And I see that the set of numbers 1 through 20 is split evenly in half between the even numbers and the odd numbers. And so we see that there are 10 even numbers to choose from. And so when we want all 3 of our numbers to be even, that gives us 10 choose 3 possible ways to do that. And as we found in example 1, 10 choose 3 is equal to 120. So there are 120 ways that we could choose 3 even numbers from this set of numbers 1 to 20. The next possibility, we're going to choose one of the numbers as odd and 2 of the numbers as even. So we're going to choose one odd number from the set of odds, and we're going to choose 2 evens from the set of evens. This is like example 5. That's 10 choose 1 from the odds and 10 choose 2 from the evens. So that's 10 times 10 choose 2, which is 450, which is the answer we got in example 5. There are 450 ways to choose one odd number and 2 evens from this set. Finally, we want to know how to choose 2 odd numbers and 1 even number, but not just any even number. The even number we choose must be divisible by 4. So the even number we choose is divisible by 4. That's these numbers that I'm circling here, every other even number. So if 2 of the numbers are odd, that's 10 choose 2, and if one of them is even but divisible by 4, that's 5 of these even numbers here, and we're only choosing 1, so that's 5 choose 1. This is like example 6, when we worked out the answer for that problem. So 5 choose 1 times 10 choose 2, and the answer was 225. Now I note here that all of these 3 possibilities are mutually exclusive. So within these 3 possibilities, no one subset gets counted twice. So the possibilities add. And the answer is 120 plus 450 plus 225 gives me 795 possible ways to choose 3 numbers from this set so that the product is divisible by 4. Next, I'm going to solve this same problem using the indirect method, and I'm going to get the same answer, 795. In the indirect method, we're going to count all of the ways to choose 3 numbers from this set so that 4 is not a factor of the product of the 3 numbers. Then, we'll subtract this result from the total number of ways to choose 3 numbers from this set, and that will give us the number of ways to choose 3 numbers from this set so that 4 is a factor of the product of the 3 numbers. And so here's my plan. It looks like this. I have to count the total number of ways that I can choose 3 numbers from this set, and then figure out how to choose 3 numbers so that 4 is not a factor of the product, and subtract those possibilities from this total number. Now, how do we choose three numbers so that 4 is not a factor? Well, all of the three numbers could be odd. That would be one way. Or two of the numbers could be odd and one could be even, but not divisible by 4. And those are the only two ways, because the moment we have less than two odd numbers, so if we have one odd number or no odd number, then we have two or more even numbers, and the product of a triple with two or more even numbers will always be divisible by 4. So having one or none of the numbers being odd does not work for us. And so just like with the direct solution, we only have three numbers that we have to compute. The total number of ways to choose three numbers from this set of 20 is 20 choose 3, and we solve for that number in example 3. 20 choose 3 is 1,140. Next, how do we choose all three numbers are odd? Well, 10 of the 20 numbers are odd, and I'm choosing 3 of them, so that's 10 choose 3. And that's a similar computation as done in example 1, and 10 choose 3 is 120. Finally, how do we choose two of these numbers to be odd, and one is even, but not divisible by 4? Well, if one of the numbers is even, but not divisible by 4, that's every other even number, like this. And there are 5 even numbers to choose from. So we want two odds, and one of these even numbers which I've circled. So that's 10 choose 2 times 5 choose 1, or 5 times 10 choose 2, and we worked out that result similar to example 6. The answer is 225. Again, these two possibilities are mutually exclusive, which means none of the sets we've counted here got counted more than once. And so these possibilities add, and then I take this sum and subtract it from the total of 1,140, and so my answer is 1,140 minus 120 minus 225, which is 795, which is the same answer that I got using the direct method. Next, let's compare and contrast the two methods. Comparing the indirect with the direct solution methods, we see that each method involves the calculation of three numbers, 1, 2, 3, 1, 2, 3, and then adding up the results to get the same answer of 795. So each method takes about the same amount of time and effort to solve the problem. Neither method seems to have an advantage over the other. In fact, the indirect method seems to involve more mental gymnastics, so to speak, because you have to think in terms of counting the subsets that you don't want to create and then subtracting that result from the total number of subsets. However, if we change the problem a little bit, then the method we choose could affect the time and effort needed to solve the problem. So we could change the problem like this. And so now we're asking, how many subsets with m elements can be formed from the set of the first 20 numbers so that 4 is a factor of the product of these m numbers? So instead of asking for subsets of size 3, we're asking for subsets of size m, where m could be any number from 1 to 20. When m is 4 or more, then I think you might prefer the indirect method over the direct method. In that case, the indirect method still involves only the calculation of these three numbers in the same way as before. But, for example, if m is equal to 5, in the direct method there are 5 possibilities to consider. All 5 numbers are even, 4 of the numbers are even, 3 of the numbers are even, 2 of the numbers are even, or 1 of the numbers is even and divisible by 4. So, for example, if m equals 5, comparing the solution for the two methods looks like this. So if m is equal to 5, and I want to form subsets of 5 elements from this set, such that 4 is a factor of the product of those 5 numbers, there are 5 ways you can do that. 10 choose 5 even numbers, or 10 choose 4 even numbers and 10 choose 1 odd, or 10 choose 3 even numbers, 10 choose 2 even numbers, or we're choosing 1 even number, but it has to be divisible by 4. That's this list again. So that's 5 choose 1, and 4 of the numbers are odd, which is 10 choose 4. And these numbers add up like this, so the answer is 14,202. But the indirect method involves the computation of only 3 numbers again, and subtracting these 2 from the total. So there are 20 choose 5 ways to make subsets of size 5 from this set. And then there are 10 choose 5 ways to choose all odds, and 10 choose 4 ways to choose 4 odds and 1 even, so that it's not divisible by 4. That's this possibility again. So the 5 choose 1 came from choosing one of these 5 even numbers that's not divisible by 4. And when I sum up these results, I again get 14,202. Check my answers and see if you agree with me. Now, why don't you try another one of these for practice? For example, how do the two solution methods compare if m is 4? You should get the same answer using either method. If you're curious, you can compare your results with my answers. Here are the answers that I calculated for every possible value of m between 1 and 20. Why don't you give 1 or 2 of those a try? I hope you enjoy. Good luck.